Now what I'm gonna do is, what I'm gonna show is that M is not maximal matching. If you assume that there's another matching M prime whose edges has more than double the number of edges in matching M. Okay. The idea is the following. So I'm gonna destroy or intersect the edges of M prime using the edges of M. Okay. And if you take on edge M, I have two endpoints, so two vertices in each edge. If I take one vertex, let's say, and another vertex from the second edge, and I connect these two things. So what I mean is using an edge from M. So using an edge in M, we can intersect at most two edges. Okay, because I have two vertices in one edge in the matching. But so let's say, let me do one more thing, and I take another edge and intersect two edges from M prime. But M prime, the number of edges, is greater than 2 times the number of edges in M. So what it means is there must exist an edge UV that cannot be covered by the edges of M. What it means is no edge in M intersects U nor V. What does that mean? Well, in fact, you can include this edge UV to the matching M. So this violates the assumption that M is a maximal matching. Okay. So this is a proof. Great. So let's get back to this theorem statement. So if you run a greedy algorithm, and what's what's important about the greedy algorithm is that it always computes a maximal matching. Okay, as long as you can add an edge, you can add it to the matching, and then you stop when you cannot add an edge to the graph to the matching set, and that gives you half approximation of the optimal size. Okay. So the second lecture is about computing the maximum matching or maximum matching. There can be multiple maximum matchings, and I'll be happy with finding one of them. Instead of like 50% approximation, I want to compute the maximum size. Okay. And the algorithm is called the augmenting path algorithm. Okay, and it has two components. So I'm gonna get to what they are. So again, you find the path and you increase the size of a matching by 1. Okay. Now the question is how do you find some certain structure by which you can increase the matching? And that part is the second component, which is called the alternating tree structure. Okay. So you find the structure using the second part, and using that structure, you increase the size of a matching using the first part. I'm gonna get to this later. Great. So again, the greedy algorithm is on 0.5 approximation algorithm, and we are interested in an algorithm that computes the maximum size of a matching. And that is the topic of lecture 2. And the central idea is about this notion of augmenting path. The augmenting is basically here it's an equivalent term of increasing the size of a matching. So we're going to construct the path, and if you have such a path, you can increase the size of a matching. Okay. Now the question is, how do you find that path? That's done by the alternating tree procedure. We're going to And the overall outline of this algorithm is called the augmenting path algorithm. Okay. And in lecture 6, we'll learn the matching problem for general graphs that are not necessarily bipartite. And that is a simple extension of this augmenting path algorithm designed for bipartite graphs. So if you follow what we covered today, you have easier time understanding or following the materials for non-bipartite graphs as well. Okay. So today's the lecture 2 is quite important, but if you have kind of there are certain parts that are not too obvious to you, I recommend when you after this lecture, I recommend you reading these lecture notes kind of in detail. Okay, but I'll try to give you the main pieces that are important to follow the analysis. Okay, but if you do have any questions, please let me know, because if you miss any of these steps for lecture 2, I guess you will lose many parts later for the next few lectures. Okay, great. So in fact, the concept of augmenting paths is quite straightforward. Let me get to that. So we have a bipartite graph and we have a matching. Okay. And given this matching M, I'm going to define this notion of exposed vertices. What it means is I have a vertex V and I say that it's M exposed. It means that it's not covered by an edge in M. Okay, so it's like, I guess couple matching system. If there's a single person who's not dating anyone, that's exposed vertex. Okay. And we say that so and there's a concept of alternating path. So the idea is basically you have a let's say an edge that is not on a matching edge, and the next edge has to be a matching edge, and you have a non-matching edge. We have an edge in the matching. You have a non-matching edge, and in fact, cannot have two matching edges consecutive, because this vertex cannot be adjacent incident to two matching edges. So this structure is not possible, but at least this alternating structure can be possible. Okay. And if you have a vertex right here that is not incident to any of matching edges, we say that this is M exposed. Okay. So we have on this is also alternating, and this pass from this vertex U and V. This is also alternating. Then what is on augmenting path? Augmenting path is on alternating path, but you have this condition that the two end vertices U and V are both M exposed. Exposed, and this is M exposed. So U and V are not covered by on matching edge. And the question is, why do we even care about this augmenting path? Well, what I can do is the following. I'll get back to this later in the next slide, but let me give you the simple idea. So instead of if you have an augmenting path like this, what you can do is the following. You can switch the rows of non-matching edges and matching edges using the as follows. You have E1, you have 5 edges. So previously E2 and E5 were matching edges. But instead of E2 and E5, let me add E1, E3, E5. Let me take those three edges in the matching, but let me take out E2 and E4 from the matching set. Okay. And the augmenting path, because it has an alternating structure, and it has both ends being M exposed, it has to have an odd number of edges. And then if you have this augmenting procedure by switching the rows of non-matching and matching, you're going to increase the number of matching edges by 1. You have 2 at the bottom, but you have 3 at the top, right? So this is the operation of augmenting. Okay. This is not creating a problem because the only status change are made to these M exposed nodes vertices at the end, because like these are already covered. Okay, so by this procedure, these vertices, middle vertices are already covered anyways, but you are just including these 2 M exposed vertices in your covered set, and then making these 2 covered is not a problem because they are not incident to any of matching edges. Okay. Any question? Yeah. So it has to be a path, right? It has to be a right. We always care about path. Sorry. A path of edges. Any other question? Again, let me just because this is the beginning of this lecture. You cannot have an edge like this because you are dealing with a matching. A vertex cannot be incident to 2 matching edges. So all the other matching edges will be somewhere located here, which are quite far from this augmenting path. So you don't have to care about the other matching edges. Okay, you need to only care about the 2 ends, and you are just adding these 2 end vertices to the cover set. That's basically what it is. Question? Is it clear? Is it clear? This is an important concept. I guess if you miss this, I guess you're gonna lose everything from now on. I don't know how to give you a easier explanation than this. Maybe I'm not. Okay. Great. Again, if you have like 2 vertices that are not covered, then by switching these things, switching the edges, I can include 1 more edge to the matching, and I can make the last 2 ends covered by the matching edge. That is the idea. Okay. So the question is, okay. So let's look at a more concrete example. So I have a bipartite graph, and this is a path from U1 and V4 are M exposed vertices. That if you go from U1, V1, and all the way up to V4, this is on alternating path. And the alternating path has 2 ends, U1 and V4, that are M exposed. So this is an M augmenting path, right? And again, you are switching these rows of black and red, then you end up with the second figure. And this is the operation called augmenting the edges, and you get a better matching. Now you have 4 edges in the matching, and then this is a maximum matching because you have 4 vertices on each of these partitions. Right? Great. So that is the idea. So again, when you have an edge, so you take an augmenting path, and if there's an edge there was part of matching, then you take it out. If there was an edge that was not part of matching, then you are included to the matching. Then that is the augmenting operation. Okay. And the idea is you always increase the size by 1 if you do this. Okay. So this suggests an algorithm. So you find an augmenting path that starts with an M exposed vertex and it ends with an M exposed vertex, and you augment the edges and increase the size by 1. And at some point you cannot find an augmenting path, then you have a proof that that's the maximum match. But that's the analysis. Well, I guess the analysis, the proof can be quite a bit complex, but that is the main idea. Okay. So in the technical term, let's define this augmenting operation more rigorously. And to do that, we need this notion of symmetric difference. Okay. So we have a matching M, and we have a augmenting path P. And the symmetric difference between M and P is defined as follows. Okay, so you are using this notation P, M O plus P. And this is a union of these two sets. So the first one is the following. So you are given a matching, and you take out all the edges from the matching. Okay, so that's because we want to reset the status of the edges over the augmenting path. Now you are adding back to the edges of the augmenting path over the augmenting path. They were not part of the matching. Okay, again, in this, we have this path P. So E1, E2, E3, E4, E5. We had E2 and E4 that were initially part of the matching, but we take out from the matching. Okay, that is this first set. Okay, now we are adding E1, E3, E5 that were not part of the matching to the set. Okay. So if you go, if you kind of, I guess, look into this symmetric difference definition, this is what this augmenting operation does. You just take augmenting path and take a symmetric difference with the original matching. Okay. So you can prove that this thing gives you another matching, and the size of this symmetric difference will be 1 larger than original matching that you can formally prove. So basically, again, if you have M augmenting path, again, this has an alternating structure, and the two ends are M exposed. It has to have an odd length, and let's say the middle one, the internal edges are part of the matching. Then you take them out, but you add the other edges to the matching. This is the former. Then this thing is no longer this path. Now this is on M alternating path, right? But you know the last two ends, which are these two vertices, are now covered. So this is no longer on augmenting path. Okay. So you can prove this thing, but I guess instead of going over the proof, let me leave it as an exercise. But I guess I already have explained the main idea behind it. So the idea is that you take the augmenting operation, and it will remain a matching. You need to argue that no two edges intersect. This is not possible. Let me. So no two edges in this after the augmenting operation. No two edges intersect. You need to argue this. And the size of this matching will be one larger than the original size. You can argue this. Let me leave it as an exercise. So this gives you on the following algorithm. So I start with an empty set for my matching. Okay. And if there's an augmenting path, okay, then we find one, and we apply the augmenting operation. We augment the edges over this augmenting path, and that's it. And you do this until there's no augmenting path. Okay. I have not explained how to find an augmenting path, but I'll get to this for the second half of this lecture. But this is the outline of the algorithm. Any question? So so you could also have, let's say, we have a P, and these two edges are a subset of this path. But you could also have edges that are not part of the path. So I'm just looking at a local structure of this graph, and you could also have other edges. But in fact, the edges that are not touching this augmenting path are not relevant. You just keep them as they are, and you just focus on the edges on the path. So I also have the same feeling that this symmetric difference is too complex to express or to refer to what we mean here. But just to kind of formalize I guess the proof and argument, let's stick to this notation. Any other question? Okay. So just for a break, so I guess I took a graduate course on graph theory for the first semester of my, I guess, PhD studies. And whenever you have a kind of exercise questions, you think about how to prove it. And then once you kind of walk through some examples, you get the idea and you understand like how to prove certain statements. But then you have to write down solutions. And what's most important is that you have to make the teaching assistants understand. But sometimes you write down some stuff in English using some, I guess, notation and stuff. You realize that sometimes what you wrote down is different from what you actually meant. That's always hard for, I guess, graph theory and combinatorics arguments. So I guess it's a good exercise to write down your own proofs instead of reading my lecture notes. Or at least you can think about like how to get the main idea and how to write down and so start writing down your own proof. Okay. All right. So great. So this is the augmenting path algorithm. So again, let's say I have a kind of efficient procedure to find an augmenting path, or that decides that there's no augmenting path. Now, what the question is, let's say I don't have any augmenting paths. Do we have a proof that I'm given on maximum matching. Okay. It's possible that even though there's no augmenting path, maybe there's a better matching. But in fact, for this situation, we can prove the following. Okay. If you have a maximum matching, there's no augmenting path. And but if you have an augmenting path, we saw that we can always increase or improve the matching by increasing the size of it by one. Okay. So let's prove this. In fact, the argument or the idea is simple for this theorem, but if you look at my lecture notes, you see kind of long paragraphs, but the idea is quite simple. So let's prove this. First of all, let's prove this direction. So I'm gonna prove the contrapositive. So let's suppose that there is an M augmenting path. Then we described that you can apply this procedure of augmenting the edges, and you can end up with a better matching. Okay. And then we may augment the edges of the path and get a matching of a larger size. So this implies that M is not a maximum matching. Okay. So this is quite obvious, but I have already written kind of consumed the 4 lines. So this is what I meant. But the idea is pretty obvious, right? By the explanation we discussed previously. The other direction is quite interesting. So let me explain that. So I'm also gonna prove the contrapositive. Suppose that M is not a maximum matching. Okay. Then there is another matching, M prime, that has more edges than M. Okay. So the idea is the following. What I'm gonna do is I'm gonna take a symmetric difference of M and M prime. What do I get? So what we want to observe is the following. So HM is a subgraph by M. So I'm gonna keep only the edges in M and remove the other ones. Then you get a subgraph. And also you take a subgraph that are spanned by the edges in M prime. You keep only the edges in M prime and remove the other ones. Then you get another subgraph, something like red. And if you have M prime, you have something like this. Okay. you get two different subgraphs. And what we want to observe is that every vertex in HM and also HM prime has degree at most 1. Again, that is because you are having a collection of matching edges, and one vertex can be incident to at most one matching edge. So if you take the subgraph spanned by only the matching edges, the degree is always at most 1. You could also have some vertices that are not matched, which have degree 0. For the vertices that are matched, they have degree 1. But in any case, the degree is always at most 1. Okay. But what happens with what about? Let me use a black color. What about H spanned by the symmetric difference? M plus has every vertex degree at most how many? Right, it cannot be 3. It can be 0, 1, or 2. Then what you can argue is the following. For any graph where every vertex has degree at most 2 is a union of paths and cycles. So any graph whose vertices have degree at most 2 is a union of vertex disjoint path and cycles. Let me give you an example. So I have M prime. Okay. But when you have a cycle, okay. Let me give you. You can also have some separate edges. But you're taking individual subgraph spanned by M or M prime. They have edges that are disconnected. You are kind of edges that are spread over the space without sharing any vertex. But if you take the symmetric difference and then look at the subgraph spanned by all those edges, then you can extend this path using this alternating structure, right? Because this part was not part of the blue matching, and at the same time, this edge was not part of the red matching. So in that case, you can just if you take the symmetric difference, all those edges survive, right? If you had an edge that were part of both red and blue, they will disappear because you're taking the symmetric difference. But it's possible to have these structures with alternating structure. Okay. So the idea is that M symmetric difference with M prime is union of vertex disjoint. Here, vertex disjoint just means that these structures, they do not share common vertices. They are kind of separated. Okay, disjoint path and cycles. What's important is that they are alternating. These red edges and blue edges, they are alternating. Okay. But another thing is that each cycle can it be odd? You have to have an alternating structure. It cannot be an odd cycle. It has to be an even cycle. It has to be even. Okay. Again, by the simple argument, if you have a red and blue and red and let's say blue, if it's a cycle of length 5, you must have an edge with red at the end later, and this cannot give you a alternating cycle structure. So every cycle has to be even with where the number of M edges equals the number of M prime edges. Let me use one more slide. So, however, we assumed that M prime has a larger size than M, right? But if you only have cycles, M prime cannot have one more edge than M, because an even cycle, even in each cycle, the number of edges in M prime and number of edges in M, they are equal. What we need to have is the following. Then we have an alternating path, not a cycle, that has one more edge in M prime than M. So what it means is we need to have a path that starts with blue, red, blue, red, blue. So this is the only structure that gives you potentially more edges in M prime than M. Cycles cannot give you more edges in M prime. Or path is the one. But the path has to have more edges in M prime than M. Again, this is M prime, M prime, M prime. And you have edges in M. Okay. We are done. We're almost done. So the last thing to observe is the following. So we are claiming that this n vertices U and V are M exposed. So we already have on M alternating path. If you have M exposed vertices at the ends, then we are having on M augmenting path. So the last step is to argue that the two end points of this path are exposed, M exposed, meaning that they are not incident to red edges. Okay. Let me give you 1 minute to argue this. This is pretty obvious, but let me give you 1 minute to think about this. Why is this on? Why are the two vertices U and V are exposed? The reason is that, well, if you had on red edge that's incident to you, well, then I'm taking a path that's already there, that's maximal. I'm not taking a sub. I was not taking a sub path. I just took this path. This is the end. You know, if you had on edge red edge incident to you, then I would have picked this one instead. So just by definition, you know, by the maximality, this is the end of it. So U and V, I mean, if they were connected to red edges, I would have included to the path, but I have included. I took just the entire path. Okay, so U and V are not connected to red edges. Okay, so this is an augmenting path. So if you forget about these blue edges, right? So blue edges are not part of the matching M. So this is M augmenting path. So we have proved the other direction, that if M is not a maximum matching, you can always create an augmenting path. You can find an augmenting path. Okay. Again, the first direction was easy. If you have an augmenting path, you can augment the edges of the path, and you can increase the size of a matching by 1. So this is if and only. Okay. Again, getting back to the algorithm, this proves the correctness of the algorithm. So let's say you start finding augmenting paths, and once you don't have an augmenting path, then it proves that the current matching is maximal by this theorem. Okay. Any question? Okay. Then for the last 30 minutes, let me explain how to find an augmenting path. Okay. Again, once we have adjusted all the augmenting paths, then we are done. Another question is, how do we find them? So before I get to that, let's talk a bit about computational complexity of this algorithm. Okay. So a computational complexity, it just gives you a measure of how complex your algorithm is, which is coming from the amount of computation you need to do to find a final answer. Okay. It's quite important to analyze or evaluate the performance of your algorithm. For our augmenting path algorithm, we're going to look into the time complexity and iteration complexity, meaning the amount of iterations we need to do to complete the algorithm. And there's this notion of space complexity. I'm just throwing away this, terminology just to, for those of you who are not familiar with this. things. Okay, you know, if you have an augmenting path, you always increase the matching, the size of a matching by 1, and you know that the maximum size of a matching can be at most half of the vertices, right? Because each edge can cover 2 vertices, so at most half of the vertices is a maximum number of a matching. So the number of augmenting paths you can find is the number of vertices divided by 2. So that means that the number of while loops of this algorithm is the number of vertices by 2. That is the maximum number of while loops. Okay. Now it's time to analyze the computational complexity of each while loop. Okay. Then the final complexity of this entire algorithm will be the complexity of finding an augmenting path times the number of vertices. That is the thing. What we're going to argue is that an augmenting path can be found in order of E time. And order of E, I mean, I guess for high school students, it just, have you seen this notation? Okay, that's good. Then I don't have to explain it. So it's just that, the total number is bounded above by constant time is what's written inside the parentheses. Okay, that's what it is. Great. So then the final complexity, then the complexity is order of V times E. Again, the complexity of each while loop is order of E, and there can be at most V number of while loops. So if you multiply them, you get V times E. Any questions so far before we get to the second part? Yeah. Okay. So that is a very good question. There's a subtle point. So I'm gonna. So this theorem, just for those of you who are interested in this subtle point, this theorem is true for not only bipartite graphs but also non-bipartite graphs. But the procedure that I'm going to explain later uses bipartition. Okay. So I need to guarantee that I have an augmenting path using this algorithm, and the correctness relies on bipartition. Okay. That is great. So this algorithm, in fact, this is a kind of basic template. And I guess the complex part is hidden in this operation, this procedure of finding an augmenting path. This outline also works for non-bipartite graphs, but the procedure that I'm going to explain will use this bipartite structure. Okay, it's a very good question. Thanks. Another question? So I guess although we have explained, I guess the most of basic graph theory materials, there are some other related notions. So I'm going to explain this notion of trees and also connected graphs. So we have two vertices U and V. We say that they are connected if there's a path between them. Okay. And we say that a graph is connected if for every pair of two distinct vertices, there's a path connecting them. Okay. It's possible that the graph is not connected. But let's assume that your graph is connected. Then a tree is defined as a graph that satisfies the following. So if you take any two distinct vertices, let's say V2 and V6 here, then there's a single path connecting them. In this graph, you have this thing. And an equivalent definition is equivalently a graph is a tree if and only if it has no cycle. So if you exclude all cycles, you get a bipartite graph. But if you exclude cycles, you get a tree. Okay. And the intuition behind it is the following. You have two vertices U and V. Then if you have two paths, you somehow create a closed walk that will create a cycle. Okay. So if you have no if there's only one path connecting two vertices, then there's no cycle, and that gives you this tree structure. Okay. And the reason why it's called tree is that it can be represented using this hierarchical representation. You take a vertex, okay, and then you enumerate all the neighbors at the next level, and you enumerate their neighbors at the next level, and you repeat. Then that gives you this kind of hierarchical structure. And the fact that it doesn't have a cycle as a subgraph gives you this nice hierarchical structure. So this is called a tree. And we say that these things are called leaves. Leaf and leaves. And the top vertex is called a root. And in fact, for a tree, you can take any vertex and have it as a root. It's just about how to represent your tree. Okay. Great. And there are this concepts of forest. If you imagine a forest, there are many trees. So forest is, so the graphs can be disconnected. They're not connected, but you can collect, this notion of connected components. What they are is that, let's say you have a graph that's connected. So even though this is not connected from a graph that looks like this, but they are, these are, if you take these pieces, they are themselves connected graphs. So if you take maximally connected graphs, they are called called connected components. Okay. You just enumerate graphs that are connected. And each of them is a tree. Then you call the entire structure forest. Okay. So they are kind of funky names. Tree, and if you include multiple trees, you get a forest. Okay. And I proved this. You can prove this. So a graph is a forest. I guess the previous statement about the tree, if you assume the tree is connected, then again, so in general, a graph is a forest, considering this continuity within your graph structure, if and only if it has no cycle as a subgraph. Just to repeat, again, if you exclude an odd cycle, you get a bipartite graph, but if you exclude all cycles, you get a tree. Okay. Of a forest. Now, let me explain this procedure of how to find of finding on augmenting path. Okay, let me start with an example, and that will, I guess the main idea is quite straightforward. once you kind of look into this example, and I'll give you some brief analysis of why it's correct. So to find on M augmenting path, so when you want to compute an augmenting path, you need to take on exposed vertex, right? If you don't have any exposed vertex, that means that every vertex is covered. Then that trivially gives you maximum matching because every vertex is covered. So if you have an augmenting path, you must have an exposed vertex. Take on M exposed vertex R. Let's say this is R. Now enumerate all neighbors of R. Because this is M exposed, all the edges that are incident to this vertex R are non-matching edges. Okay. If any of them are M exposed, let's say this is vertex V. If this is M exposed, that means that we got an augmenting path of length 1. So these two vertices are not covered. You can match these two vertices. This is an M exposed vertex. This is an M augmenting path. So let me write it down. If one of them is M exposed, we get on M augmenting path. Otherwise, all the neighbors are not M exposed, then we can take an edge from the matching M. Okay. Otherwise, for each neighbor, find the matching edge covering it. Now, you take this vertex at the next level and you repeat the same thing. You enumerate the neighbors. Let me take this vertex. Now, each vertex can be part of at most one matching edge. So the edges below, they have to be all non-matching edges. So they are all black edges. Again, if you have an M exposed vertex V, if this is M exposed, then you get an augmenting path. Right? If not, you can add on edge from the matching below. And we repeat this procedure. And this is basically the alternating tree procedure. Any question? So once you are done, then you either find, okay, and then repeat. once the search is done, without on M augmenting path, we can argue that there's no augmenting path from R. Okay, and that to prove that we need to use the fact that the graph is bipartite. Again, but let's say the search is done and you cannot find the augmenting path. What you do is you remove this tree structure completely from the graph, and then you start with on another M exposed vertex and grow the tree from there. And remove all vertices of the tree from the graph. Yeah. And so this is on so I guess augmenting path. Let me use this slide. So this is on M augmenting path of length 1, and you can have length 3. It doesn't have to have on edge in front of the matching. So as long as you start with a non-matching edge and you end with a non-matching edge, then this is augmenting. You can have just one or single edge, but this is not augmenting. Yes. Okay. Any question? Now, for later references, I'm gonna refer to the top one, and I'm gonna use even level and odd level. So this is even. The next level are odd level vertices, and I'm gonna also use even vertices. If you look at this this figure, only the vertices from an even level can have many branches, right? And at an odd level, you can have one branch using a matching edge. Okay, just remember this structure. I'm gonna get back to this later, but this particular and then what I'm saying is this tree, it has some specialized structures, and that will be useful to analyze the algorithm. All right. Let me just formalize what we explained using this pseudocode. So I have a bipartite graph and a matching, and then you have you find on exposed vertex, and you set it as a root, and so this L refers to the set of leaves. Like if you look at this thing, these are all leaves. Now they can be the starting point for expanding your tree. Okay, I'm gonna keep this vertices at the bottom level, and that's just the set L. And so until you have something to explore, you take that and you enumerate all the neighbors. And if you find an exposed neighbor, that gives you an augmenting path. And if you do not, you add on matching edge. Okay, you take a neighbor, and if it's matched, you add on a matching neighbor, and repeat. This is the algorithm. Okay, so the algorithm builds a tree structure like this, and if you have if you find the exposed vertex, that gives you an augmenting path, And again, let's say if you have a vertex like this, that gives you an augmenting path. Like this, like this. And if you do not, then you just have a kind of tree structure without this kind of small branches in the middle. And this is called an M alternating tree. Okay. So if you stop searching and you get on kind of alternating tree, and if you didn't find an augmenting path, again, then you just that we can argue that there's no augmenting path, including R. Just remove this tree structure completely, and you start with another exposed vertex and grow an alternating tree from that, and you repeat this process. Okay. What you can prove is the following. So if your graph is bipartite, then the algorithm must find an augmenting path if there's one. And the structure doesn't, if the algorithm doesn't find an augmenting path, then it means that it's on maximum match. So this is the second important component of today's lecture, lecture 2. So in fact, lectures 3 and 4 will go back to this, proof idea and analysis. So, I want you to read through the proofs kind of one more time when you go back. Okay. But let us go through the proof together. So, let me actually take this thing. Take a screenshot. Okay. Copy. Again, I have on even and even vertices and even vertices. And I have odd level vertices. So if your search is done without finding an augmenting path, then this tree structure can be simplified into this kind of weird figure. And here W1, so just the subscript 1 refers to the first tree. Okay, the W1 is the set of even level vertices. V1 is the set of odd level vertices. Okay. Again, so R1 is adjacent to some neighbors. And it goes to the next level using matching edges. And then this is a vertex from level 2. And then you enumerate all neighbors. And the neighbors are at an odd level 3. Now you take a matching edge that are connected to these vertices, and you go to level 4. Okay. Note the size of W1 is 1 larger than the size of V1. Okay. This is because level 2, level 1, which is the first order level. Let me use different color. the size of level 1 is equal to the size of level 2. Right? Because if you look at this tree structure, when you go from an odd level to the next level, which is even, you're always using the matching edges. So level 1 and 2 have the same number of vertices, and also level 3 and 4 have the same number of vertices. But we have this root node, root vertex, that gives you one more vertex in the set W1. Okay? Any question? So this is good. And one more thing to observe is the following. And this is the part where this bipartite structure is used. Okay. So I have claim a property 1 is that the size of this set W1 is 1 larger than the size of V1 from the odd levels. Another claim is the following. No two vertices in W1 are adjacent. So why is this true? Let's have a graph. So we have an odd level, and let's say I have even level. Okay. So if there's an edge between two vertices from an even level, let's say I have a edge between these two, then I get an odd cycle. I have the proof is let's say suppose not. Then there exists UV from an even level with UV is an edge. Then moreover, there is an even length path from R to U, just because U is at an even level, and also V. So this is even length. This is another even length path. But the length of the edge between U and V is 1. So you get an close walk of an odd length that gives you an odd cycle, and that destroys this bipartite structure. Okay, it's good. So we don't have an edge between two vertices in W1. Okay. Great. So this is it. And let's say I don't have any augmenting path. That means that I delete the first tree, and then I get a second tree. And if there's no augmenting path, I get a third tree, and so forth. And then you stop until you remove all vertices from your graph, and you conclude that there's no augmenting path. Okay, so you are left with this structure. Then the last point is the following. So the claim, okay. So, and then, okay, so this is the graph. Now what I'm gonna do is the following. I'm gonna collect these vertices from an odd level. And I'm also take the other vertices. So they are coming from some even levels of some trees. Then the claim is that no two vertices in W1 through WK are adjacent. So this is the last thing. I'm gonna finish in 5 minutes. Sorry about going over. Let's get back to this figure. Let me. In fact, the region is simple. Let's say I have two vertices from different tree. So I proved that no two vertices from this black set, if they are coming from the same tree, we prove that there's no edge between them. Otherwise, you get an odd cycle. So if there's an edge between any two vertices at the bottom, they must be coming from different trees. Let's say I take the first and the last tree. Let's say there's an edge between them. Okay. Then this simply violates our assumption about this the procedure of extending the trees. What it means is, let's say you are done with this tree, and the reason why we are done with this tree is that we cannot grow the tree anymore, right? But if you have an edge between this thing and this thing, somehow this vertex will be, let's say this is some even level vertex. Okay, and I have on, and then the reason why you stop here is that again you cannot extend your tree structure. But let's say I have a edge between this one and a black vertex right here, which itself is connected to a matching edge. I'm assuming this thing. Well, then you can just include this thing. You can bring this edge over here. And instead of this green edge, you can extend your tree by adding this edge. So this simply violates our assumption that your tree is maximum. So this green edge is not possible. Right. And that's why this thing. So no edge is. So this proves this claim that if you have an edge, that should touch top vertex right here. You cannot have an edge that's fully contained at the bottom. Okay. One end has to be touching the top vertex. You can also have an edge that's fully contained at the top, but no edge that's fully contained at the bottom. Okay. This is it. So we are almost done. So okay, let's say every edge is incident to a vertex in V1, V2, and Vk. Okay, and every edge can touch at most two vertices in V1 union Vk. And the structure here in this graph setting is that for every single vertex, we are adding, one matching edge. So basically, we are adding as many matching edges as possible from the top set. So this is the argument for why the current structure is the maximum possible. Okay. So this is the proof. Let me go through this proof, the last bit of the proof again tomorrow. But this is basically the proof. So let's conclude the lecture by talking a bit more about complexity. So, we are enumerating, we go through each edge at most once. We include the tree structure. And if the tree is found, we are removing all the edges or vertices from the graph. And then we move on to the next graph and we start searching. So each edge can be enumerated at most once. So this alternating tree structure can be found in order of E time. So this is the proof for the complexity. So again, the number of while loops is at most the number of vertices, because finding on augmenting paths will always increase the size of a matching by 1. And so the total complexity is V times E. Okay, let me repeat the alternating tree structure just one more time, and in 1 minute, and I'll conclude. Again, we take on exposed vertex in the hope of finding an augmenting path containing this exposed vertex, and then we extend this alternating tree structure. If we find an augmenting path, then we are done, we are okay. And if not, then we have a tree structure, and with the property that there's no edge between two vertices from an even level. Okay, and then we also prove that there's no edge between two even levels from two different trees, and that will give you this graph structure. And it has the property that no edge is fully contained at the bottom, and every edge has to be incident to at least one vertex from the top. And if you look at this last bit, the matching is the size of the matching is equal to the size of the top vertices. And then this basically proves that the current matching structure is maximum. Okay. And I'm gonna get back to this later tomorrow. Let me conclude here. Thanks.